So welcome back. So we are in our last lecture of week 4, and where we will try to talk about the better RNN units. So typically, better units have been proposed at GRU and LSTMs, and we will focus mainly on LSTM in this particular lecture. So we will first talk about what are the issues with vanilla recurrent neural networks, specifically the vanishing gradient problem, and then how do you use gates for getting better units of RNN. And that's where we will talk about LSTMs that became much more popular like just before transformers. Even around transformers they were quite popular. So we were not using RNNs by default, but LSTMs. Right? So what are those models? So this is what we will discuss in this lecture. So first of all, what is the problem with the recurrent neural networks? What is this vanishing gradient problem? So what happens in the recurrent networks? So when I am showing this slide, so you can read as per notation, these are the U matrix, right, going from hidden to hidden, but just to take the point, right. So you generate hidden state at each step in the RNN. So for the first token x1, x2, x3, x4, I generate the 4 hidden states, right. And you may be doing language modeling, where that means you have loss computed at every step. So you would have a loss at this step also, J2 in your parameters, at this step also J3 theta. Now you get the loss, say cross entropy loss at each step. Now you accumulate the loss and you back propagate through time, BPTT, you do BPTT to update all your parameters. So that means this matrix, call it W or U, will be updated based on the loss that you have at this point. So you should update this matrix based on the loss, but this parameter also has contributed to this. So based on this loss, you have to also update this W, and you have to also update this W. And same thing you have to do with all the losses. So based on J3, you have to update this W and this W. J2 will only update this W, because others are not contributing to J2. This is only left to right, right. So that means if you think about a far away, I mean slightly longer time sequence, so the loss that you have at this point would be coming from all steps before, and all these versions, right, of the same W, like they are the same W, same parameters shared across, would be updated like differently as per this loss. But you want them to update so that you can get signals from far away points in the time sequence series in the whole sequence to impact your current output, right. That is why you wanted to use RNNs, so that you can use any long sequence. So I want any word, even the first word, to contribute to a very far away loss, right. So that means my gradient signal should pass and go to each word or each of the W, and same thing happens with these matrices that you have from input to hidden. You have to pass the gradient signal to all of these matrices. Now, how is that computed? So we talked about chain rule, right. So suppose I want to see what is the what will be the contribution of loss as per DH1, right. How would I compute it? So this will go through entire this sequence. So this will be, so I can say, okay, H1 depends on H2 depends on H1. So I will do DH2 over do H1. Similarly, do H3 over do H2, do H4 over do H3, and do J4 over do H4. So just by applying chain rule, I can compute how much would be the impact over H1, right. Now in each of these, I will have right. So I have to multiply all of these, right. I have to multiply all of these uh, values to get the contribution that the loss is having over, or H1 is doing over the loss, so that I can update parameters, right. Now they all will depend on this matrix W, right. So we can do this math, but so you know this H2 depends on some nonlinearity sigmoid or say 10H, and in this case I am just writing W, it was U in our notation, WH1 plus something on input plus some bias term, right. And when I do this differentiation, I will have a term because of 10H, but then because of this I will have something that depends on W, right. So it will depend on the magnitude of this determinant W. Right. And now this can be, the parameters can be such that it can become very large, it can become very small, right, because you will keep on multiplying with this, I mean at every step. So you may have W to the power 4, 5 as per the number of steps. Now it may not always be 1, right. It may either become larger than 1, it may become less than 1. So if it becomes larger than 1, this is called a standard exploding gradient. If it is larger than 1, like the entire thing, but just to keep it simple, so this becomes exploding gradient. So you'll have a very large gradient, and you don't want that. So the trick is easy. You can do gradient clipping. So gradient clipping means you will simply put a maximum on the magnitude, If it is beyond that, you clip it to that maxima, right. So it's called clipping. You retain the sign, but the magnitude will not go beyond a certain threshold. So that is easy. The problem happens when this is less than 1, maybe less than, very small one, than 1, smaller than 1, and you are taking powers of this W as you are going over multiple steps. So it will keep on diminishing, right, and it may even become something less than the precision of the system. It may even be 0. So what will happen if it becomes really 0? So when these are really small, so the gradient signal keeps on getting smaller. You can see from this picture, keep on getting smaller, smaller, smaller. So it may not even reach to some faraway states, right. So it may not reach some faraway states. It may become 0, so they will not be updated based on the loss at a faraway state, right. Okay, but why is that a problem? Why is that a problem? So what is happening? Gradient signal from far away is lost because it is much smaller than. So what will happen? You will still update this particular. You will get the updates for this W based on the loss in the nearby step, but you will not get much signal from a far away loss, right. So what will happen? Model weights are updated only based on some near effects, but not the long term effects, right. So long term effects are not captured. The impact that this has over this is not captured. Impact of that this has on this is captured, right. So far away, the long term effects are not captured. Now why is that a problem in the language? So here are some examples, like what can happen in a language, right. We also talked about this earlier. So you cannot define the context window very easily, that I will only update this word depends on the previous 7 words or 6 words. So let's read this sentence. So when she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her, and we can get, okay, she had to print her tickets. So it should be tickets in this case, right. But you think about how many steps back you have to go. So you have to go, there may be 20 or more than 20 words right in between. So you have to go that many words back to be able to use that. Now, so that means RNN model has to model dependency between tickets on the 7th step and the target word tickets at the end, and that is a very, very long term, right. So, but if the gradients are small in the long term impact, your model cannot learn this particular dependency. It will only learn the recent words, close enough words, right. So it may actually end up printed her toner or printed her stationery, rather than saying printed her tickets. Right? So the model becomes unable to predict similar long distance dependencies at test time, and that becomes the impact. And we don't want that. We want it to be able to predict based on whatever context it has available, right? So this is already in the input, so it should be able to make use of the long term effect, but in practice it does not. So, and that creates a problem. And this is another phenomenon called, say, syntactic recency versus sequential recency. So many times I've seen students make this mistake while writing. So you have the writer of the books and you have to fill in this blank. So you say, okay, you will typically use R because that is based on the syntax, the sequential recency. The previous word was plural, so you typically end up writing R. But in general, you have to see the syntactic recency. So you say, okay, so this should depend on the actual word writer, and I will say writer age. The writer of the books age is correct, but the writer of the books are is incorrect. That is only sequential recency. I want to capture syntactic recency. Right. And this becomes possible only if I can capture the long term impact of the dependencies in recurrent neural networks. Now, how do you fix this particular issue? So the main problem is that suppose at some time step, say when you say tickets, you had some hidden vector for tickets. Now what is happening every time? Next time step I plus 1, again a new word gets fed, and this gets multiplied to matrix U. So U times this previous step plus W times the new input computes the new state, and then you apply some nonlinearity tan h. So there is a complete change from the previous time step h t minus 1 to h t. Now if I want to say I want to preserve some information, there is no easy way to preserve some information. I say I want to use this information for longer time period, there is no easy way, right? There is not even functionality for doing that. You are multiplying with large matrix and again applying nonlinearity, so this will be lost, right? It will be completely transformed, right? But suppose I want to preserve information, right? Say this is 100 dimensional, I want to preserve information since of say 5th dimension, 25th dimension for some longer time steps. This is not even possible with the recurrent neural networks. So how do we make them equipped with keeping the memory, some sort of memory, right, over longer time period? How they can keep memory over longer time period? So we need some better RNN units. That's the idea. So what RNN units do, better RNN units do, they make use of this concept called gates. And gates are also vectors. It is not so they apply various gates. So on each time step, each element of the gate can be either open, closed like a gate, or somewhere in between. Typically, you can visualize them as either open or closed. Very rarely they will be somewhere in between. And the gates are dynamic, and their value is computed based on the current context. And there were two very famous architectures, I mean, that have been there, which are using these gates, GRU and LSTMs. In this lecture, I will only talk about LSTMs, but you can read about GRUs. The GRUs are called gated recurrent units. So we'll talk about LSTMs. So what will happen in an LSTM? So you see, so first of all, before I talk about that, you have to see this LSTM also as a box where you are, or a GRU as a box where black box. So you are given the previous hidden state ht minus 1 and the current input xt, and it gives you a new state ht, right? New recurrent state. Now inside you can use RNN, you can use GRU, you can use LSTM, right? So they have the same functionality. So in the entire picture, you can just feed LSTM instead of RNN. It doesn't change anything else that we talked about in different paradigms and so on. Right? You can just replace RNN wherever we said within LSTM, and it will still work. Okay. So but what actually happens in LSTM. So, on any step t, you have a hidden state HT, plus they introduce something for memory called cell state, which is cell state CT also, and they are both vectors of length n, assuming your hidden vector is length dimension n dimension HT. You also have some sort of cell state memory of n dimension, and this cell is used to store long term information. Okay. Now, what LSTMs can do, it can read, erase and write information from the cell, right. So, they would be using this to capture what was the information before, let me use that to compute the new representation, to compute the output, and then retain some information from previously and add new information. So, you can read from this, erase it and write new information over CT. Now, how do you select what to read, what to erase, what to write? Will you do it manually? No, it will be depending on some parameters, right. So, it is again controlled by different gates, okay. And gates are things, their values are calculated by probabilities. They are other parameters that compute these gates. So, the parameters will control what part I will erase. So, if I really need for this problem this particular part, these dimensions of my cell state, I will retain it. If I do not need it for later on, I will just forget these and keep new information at those dimensions. Okay. So, this is one way you can visualize LSTM. So, again you see it is a black box, HT minus 1, XT is input and you get HT, right. But then there are many more things that are happening. So, you have a new thing called cell state. So, you feed CT minus 1, you get CT, right. In between, whatever happens is controlled by many gates. So, there are 3 gates. So, there are 2 gates that control how much you will forget from the previous cell state, right. So, you have a forget gate. So, again they have the same dimensions as the cell state. So, suppose cell state is n dimension, CT minus 1 is n dimension, your forget gate will also be n dimension, FT will also be n dimension. So, it will tell you, suppose somewhere your value is 0. So, you will multiply it with the previous state and you will say, okay, that means I have forgotten that, right. Suppose I was storing 1.5 in this particular dimension, but if I forget get it 0 at that point, I will forget that, right. But if it is 1, I will always retain this minus 0.25, it will go as it is to CT. So, CT will retain this 0.25, but it will forget this 1.25 and it can write new information there. That is the idea of the gate. It can control whether you want to retain some information, erase it and write new information. Right. So, that is what, for example, forget will do. Similarly, you have input gate. So, input gate will control, so whatever is the new cell content. So, you will again compute what is the new cell state, like you were doing for the recurrent, you will compute the new cell state, what part of this will actually go into the new cell state. So, again IT will again be like gate and you can just visualize them as 0 1s. So, here you can have, suppose it was 0 and let us say it was 1. So, what will this do? So, you have anyway erased this information, but now you will write whatever came in CD tilde, whatever new information came in. So, 0.3. So, this 0.3 will get written in CD minus 1, this will get this 0.3, the new information. So, input gate will tell you, okay, if it is 1, it will completely take the new information. If it is 0, that means whatever is the new information that you computed will not go into CT. If input gate is 0, this will not go into CT. Same for forget gate. So, input gate and forget gate will control what part of the previous cell state you will retain and what part of the new information you will capture in your CT. Right? That is how you get your CT, by using forget gate, input gate. Then how would you get HT, right? You only talked about CD minus 1 to CT. So, what do you do with HT? So, you say, okay, so I have my new cell state, maybe some dimensions of this are relevant for my output and some dimensions are only relevant to capture information for next time step, but are not needed for the output. So, what I will do, I will have an output gate, I will have an output gate that will control what part of CT, maybe CT had certain dimensions only. So, these dimensions are important for my output. So, OT, what it will do, it will be 1 for these. So, OT will be 1 for these and 0 otherwise. So, it will control that I will take these dimensions and use that to compute my HT, the next state. So, I will simply use that, and this is used for my output HT. If I am doing named entity recognition, I can multiply this with a matrix V, take a probability vector, do softmax and whatever, right. So, HT is used for computing output, right. So, what part of CT is important for my output is controlled by the output gate. So, 3 gates: forget gate, input gate, output gate. Forget gate and input gate control how do you compute from CT minus 1 to CT, and output gate controls how do you get from CT to HT, right. So, in terms of equations are very similar, right. So, if you know the normal RNN equation, you just change the subscript. So, the parameters are not shared by default. So, forget gate is nothing but, so you have HT minus 1. So, you have U HT minus 1 plus W XT normal equation, but you use some subscript F, UF and WF, and you use sigmoid for gate, because sigmoid is like a gate, right. So, it remains roughly 0 or 1 for most of the time duration. Very rarely it goes between 0 and 1, right. May not be a very good picture, but yeah, you get the point. It remains either 0 or 1 for most of the time step, and very rarely it goes between 0 and 1. So, sigmoid is a good way to maintain a gate or get a gate. So, similarly input gate, right now I can write the equation. So, now I will UI and WI. So, you have 2 more. So, more matrices, apply sigmoid gate, I get input. How do you get the new cell content? So, there I go to my equation like I had for the RNN. So, I have a new UG and WG matrices. So, UG times HT minus 1, WG times XT, and I apply tanh nonlinearity. I know I do not need a gate for new cell content. I can use sigmoid anyway, but just to distinguish, I do not need a gate here, right. So, this is my new information. This I was calling as CT tilde. So, here I am writing it as GT. And now, you have your CT minus 1, the previous cell state, and the new information. You control how much you will use of these using forget gate and input gate, right. So, this is an element wise dot product. So, this is element wise dot product. So, idea is that if FT is 1, somewhere that means you forget that information in that dimension. It is very important in that dimension, because FT is not a singular value, it is a vector. So, FT I is 1, in ith dimension it is 1, that means in ith dimension you forget the information, but there are other dimensions also. So, FT may have values that are 1, 0 and also in between in various dimensions. Similarly, for IT, if IT is 1, that means you would use the information from the cell state. If IT is 0, you will not use the new cell content at all to get your new context vector, new cell state. Okay. What else is remaining? Your output gate. You can write the equation for output gate. So, OT will be nothing but sigmoid UO HT minus 1 plus WO XT, right. Just new subscript, you have a OT, the output gate, and output gate will control what part of CT will go into HT. So, this is my output gate, and the new hidden state will be OT element wise multiplied to tanh of the cell state, right. So, that means OT will control which dimensions of my CT would be used for my new hidden state, and this hidden state will go to my y hat t, the prediction that I am doing at the time step. Right. It will not come from cell state, but will come directly from the new hidden state. And that is how is the LSTM equations, right. So, what happens compared to RNN, you have much more parameters, right. So, you have much more parameters. So, like you can see you have 1, 2, 3, 4. So, you have 4 U matrices and same 4 W matrices, but because your H is of the same dimension, so So, you have only one V matrix. So, one V matrix for your output. So, it is not directly 4 times the parameters of RNN, but U and W are 4 times and V just 1 times. So, this can tell you how to find the number of parameters you would use for LSTMs. So how does LSTM solve the vanishing gradient problem? So, what we have seen, LSTM would help you in preserving information over many time steps, because now you are not saying that okay, all this information in CT minus 1 will be multiplied by a matrix W. No, you are controlling it by gates, and if your input gate is 1, the forget gate is 1, sorry, so forget gate is 1 in this dimension, you would retain this information. So, there is a facility now, right, by which you can retain some information over many time steps. This facility was not at all there with RNNs. Right? This is coming through use of gates in the LSTMs and other similar units. So, if the forget gate is set to remember everything on every time step, then the info in cell is preserved indefinitely. Right? You can do in everything, or you can use on certain dimensions. You may remember information from certain dimensions only, but you can do it over many time steps if your parameters are according to that. Right? But in RNN it is very difficult to because U will be multiplied to H. So, it is very difficult to preserve information in the hidden state, because you are multiplying U with HT minus 1. So, there is no way you can say I want to preserve information in a particular dimension. No. Till certain point, then you want to forget that much functionality facility is not there. Okay. And you can try this problem to get more idea about parameters. So, see, I said you can, wherever you use RNN, you can use LSTM. So, here you are using a bi LSTM. What does that mean? You have forward LSTM and you have a backward LSTM. Same functionality. So, you will get an HT in forward direction from here, and you will get an HT in the backward direction from this. Okay, just like you got in RNN. So, suppose using bi LSTM for language labeling in code switch data. That means you are mixing multiple languages. So, let us say English, Hindi. There are 5 possible languages tag per word. So, it is not a span problem. Each word has at least 1 tag. So, I just have 5 labels for my output. So, output layer is 5 dimension. So, y hat t is 5 dimension. If y hat t is the vector, it is 5 dimension vector. Each word has 50 dimension embedding. So, input is 50 dimension, and the hidden state for both the forward and backward are 40 dimension. So, H is 40 dimension, both forward and backward. So, how many parameters you will need, right? Let us compute a forward, right. So, there are, it is LSTM. So, we need 4U, 4W, 1V, right. Because you simply concatenate in bi-directional, I can just compute forward and backward and add them, and this would work. So, parameters for forward. What is the dimension of U? U is U is from hidden to hidden. So, hidden to hidden U is 40 cross 40, and W is from input to hidden, that is 50 cross 40. So, 4 times this, 4 times this, and V is from hidden to output, that is 40 cross 5, your output is 5 dimension. This becomes the forward LSTM. Backward LSTM would be exactly the same in this case, right. Bidirectional, your hidden state will become, combined hidden state will become 40 plus 40, but we have anyway captured that in 40 times 5, 40 times 5, 80 times 5, right. We are adding them separately, and this will give you the total number of parameters in a bi LSTM, right. Very, very similar, except that you have 4U and 4W matrices, rather than having 1U and 1W matrix in the normal RNN. Now, this brings us to an end to recurrent neural networks. Now, question may be, fine, what is the problem with this architecture? Like, why do we have to go beyond RNN? So, one issue that happens with RNN is that for distant words, so think about this sequence, the chef, who, and then you describe the chef, and then you say watch, right. So, you want to learn this watch depends on the chef, Yes. So, I have to learn this long distance dependencies, and we saw there is a vanishing gradient problem. Even if we use LSTM, it increases this functionality a bit, but still it is not the best. You have to still go through every step, and you have to ensure that this information is preserved over so many time steps, right. So, you are always doing computation in a linear order. So, you are always going the chef who in a sequential manner, and the question may arise, is this the right way to think about the sequences? Do we always have to go in a linear order of words? Can I do something different? Can I always have a direct connection from chef to here, right? That may be that would be better, right? In this case, if watch could have directly attended to chef, directly connected to chef, that would have been better, but that's not possible in the case of RNN or LSTMs and so on. And this creates a problem in that I cannot parallelize the computation. So, because what will happen, see, if I have to compute HT, I have a sequence of size t or t minus 1, I have to compute HT. To compute HT, I need HT minus 1. In my equation, I need HT minus 1 before HT, and before HT minus 1, I have to compute HT minus 2, and so on. So, there is a dependency. So, even if I am taking a long sequence, I have to do one by one. I have to compute H1, H2, H3, H4. I cannot do in parallel, and this creates some hindrance in training it in not very large data sets. So, I cannot parallelize this whole computation. Okay. So, is there some other way in which I can do this computation so that it can be parallelized? That becomes another intuition, and we will see that the next week. In the next week, we will see the architecture like transformers can help us in solving these problems. So, people have recently even applied and tried to get better LSTMs by taking insights from transformers and other models. So, this was a paper very recently from 2024, where they have modified, revamped LSTMs, and they called XLSTM. So, this is the typical LSTM where you have this solid state, does this constant error carousel. I mean, this is helping us to retain some information for long time period, sigmoid gate and so on. But they introduced new cells like memory cells, which do exponential gating, new memory mixing, and do matrix memory, parallel training, and so on. They use various new things and create these new blocks, and they have given this architecture LSTM, and you can go and read about this, but this would need much more background than whatever we have covered till now. Okay. So, with that, this ends the recurrent neural networks and LSTM part of week 4, and we will go to transformers in the next week. You can again go to chapter 8 of our book to get more idea about the topics we have covered in this lecture. So, thank you.